Good morning, dear participants. I'm very happy that you have logged in at the right time. Our speaker is already with us, and our delegates are also with us, and many of them are still joining. We've been attending this Saturday webinar series titled Excellence in Teaching, Training and Research. We've been hearing lots of expert lectures from the field of teaching and in the field of training and in the field of research. Today we have got a very nice resource person with us who has consented to spend his busy schedule, with us actually. Today's topic is indigenous materials for energy storage. In line with our technical lectures, we have heard about microplastics. We have heard about investment casting last time. And today we are going to hear about energy storage. This topic, regardless of our backgrounds, is very, very important and very, very relevant to the current scenario here. And we have got Dr. Manohar from Indian Ceramic Society with us. And we have the speaker, Dr. Srinivasan Anandan, Scientist E, Center for Nano-materials, International Advanced Research Center for Powder Metallurgy and New Materials, ARCI, with us. We welcome you all, sir. We welcome the delegates on behalf of Bharat Institute of Engineering and Technology, CRESIHRD, and Indian Ceramic Society, Hyderabad chapter. And I heartily welcome the audience who have been attending regularly these kind of lectures on all Saturday mornings. Thank you very much. I request all of you to stay in a proper place and turn on your video with official decorum and kindly pay attention to the lecture. It is not so easy for us to meet Dr. Anandan and listen lots of things that are most upcoming thing that is happening in India. We cannot know the real status of the energy storage materials and the challenges and bottlenecks involved. And if you want to do some research on it, where to start, how to start, and all those things cannot be obtained from anybody here. So Dr. Anandan is very friendly, and even when I was a project knowledge officer, whenever I had to read and know about lithium-ion batteries, I could go and get his appointment and I could discuss. Even if I had to discuss even for 10 and 20 minutes, I used to get the full scenario of the subject. It was very useful for me. And today, all the speakers have got that opportunity. I want you all to listen, paying attention. And at the end of the session, you can post your questions in the question and answer session in the chat box. Now, let's start the webinar. I welcome Dr. Manohar to address the audience and welcome the speaker. Over to you, sir.
Thank you, Dr. Sophia Rani. Before introducing the speaker, let me thank and greet the audience. I am very happy at this tremendous response. It shows that people who are in the research field, they want to learn new things. They want to try out new things. They want to try out radically new ideas. This will very much help in our India's progress. This topic, uh, indigenous material for energy storage, is also quite important because nowadays fossil fuels are running into extinction and we have to depend on renewable sources like solar energy and wind energy. Problem with these is that they are intermittent. So without energy storage, they are useless. So along with development of these two fields, energy storage field is also important. We have to find new materials for energy storage, new ways of energy storage, and new methods how to implement that energy storage into various processes. And today's speaker will throw light on that. And along with that, indigenous development is also important, because we can't go on depending on China or foreign countries for various raw materials or devices. Dr. Srinivasan Anandan is a scientist in Nano-materials group of ARCI. He did MSc, MPhil, and PhD from Anna University, Chennai. And after that, he went to Japan to do postdoctoral research. After that research, he kept on working in Japan as a research scientist, and then uh, as a member. His special fields are various battery storage devices based on lithium, then photocatalysts, superconductors, synthesis of porous materials, etc. He has 20 years of experience. Um, he his output is tremendous. He has published 68 papers, and he was also invited to give invited lectures and to address various conferences. He has filed for 17 patents. He was involved in three technical transfer projects which have been commercialized. He has worked, the 9 research projects have been completed under him. Um, he has written 3 book chapters and also 3 conference proceedings. He is a member of various societies, and for his tremendous work and glittering work, he has been duly awarded. He is an associate fellow of Telangana Academy of Sciences. Then he is a member of MRS Japan, and he has been awarded Scientist of the Year award by Stanford University recently. So with this introduction, I invite the speaker, Dr. Srinivasan Anandan, to address the gathering. Thank you.
Thank you, sir. Can I get permission to share my screen? Yes, thank you. Are you able to see my slides? Yes.
Yes.
So, very good morning to all of you. First of all, let me thank Dr. Manohar, Secretary, Indian Ceramic Society, Hyderabad, for giving kind introduction about me. And I extremely thankful to Dr. Sophia Rani for inviting me to deliver a lecture on this international webinar. And then as she mentioned that when she was associated with the ARCI, we had a good association with her, and then she was very helpful for doing all the systematic pattern search which is relevant to our material developmental activity. She is so sincere and then hardworking person. So we really enjoyed working with her, and I really thankful, madam, for inviting me to deliver a lecture on international webinar. And I also thank my colleague, Dr. Sendil Kumar, for inviting to deliver lecture on this that webinar. So I'm very glad to be part of this event, and I wish you a great success of this event. So coming into my presentation, the title of my presentation is Development and Demonstration of Indigenous Material for Energy Storage Application like lithium-ion battery and then supercapacitors. As all of you know that we are extensively using all the electronic gadgets, and then recently we started using that all electric vehicle. If you know that the heart of the component for this all the electronic gadgets and then electric vehicle is the battery. So since each one of us are using this all that electronic gadgets and then electric vehicle, there is a huge requirement for this battery. Unfortunately, in India, we don't have that single company to manufacture this lithium-ion cells. So there is a huge requirement. That is the reason the development of indigenous material or lithium-ion cell, which is relevant to that electric vehicle technology, is the need of the hour. That is the reason ARCI, we have been focusing on the development of indigenous material technology as well as lithium-ion cell technology, which is suitable for electric vehicle application. So I'll be covering that what are all the various developmental activity which we are doing at ARCI related to lithium-ion battery and then supercapacitor in my presentation. So let me briefly explain about my institute. ARCI is International Advanced Research Center for Powder Metallurgy and New Materials, which is autonomous R&D institute, comes under Department of Science and Technology. So the unique mandate of ARCI is transforming laboratory research into technology and transfer the technology to the industries. So ARCI has in operation of 11 centers of excellence, of which 9 centers are located in Hyderabad in its main campus, and then 2 centers are in Chennai. So in ARCI, we mainly focus on the development of material and new process. Subsequently, we work on that upscaling of developed process at lab scale and the fabrication of prototype. And then later, we demonstrate that the prototype for that field application and transfer the technology to the interested industries. So this slide shows that outline of my presentation. I will start briefing about that energy requirement and importance of energy storage system. And then I'll be highlighting that the usage of this lithium-ion battery in that electronic gadgets and electric vehicle application, followed by the research and developmental activities of lithium-ion battery and then supercapacitor, which we are carrying out at ARCI, finally by conclusion. So this slide is familiar to all of the audience. Whatever the current energy requirement is met by the fossil fuels. As you can see that the pie chart, the major contribution it is coming from that burning of coal, natural gas, and then oil. Yeah. So the major issue is when you are meeting this the energy demand using these fossil fuels, the availability of this fossil fuel is very limited. For example, oil is available for 30 years, natural gas for 60 years, and then coal for 200 years. But if you can see that our energy requirement, so currently the energy requirement is 13 to 15 terawatt per year. But if you can see the future energy requirement, nearly 30 terawatt, nearly double the requirement of what we are using right now. But if we are having that limited fossil fuel sources, then it is a big challenge. And then we are forced to move out from that fossil fuel to renewable energy sources to meet our energy requirement. Other major issue is when you are using that fossil fuel, lot of green gas emission it is happening. As per statistic, we are the 4th largest producer of CO2 in the world. We are emitting nearly 1.34 million metric ton per year. That is huge amount. There are 2 things. One is we have to move from that fossil fuel to renewable sources because of depletion of fossil fuel and then change of climate, that the global warming, whatever, all the issues happening because of that burning of all the fossil fuels. Other thing is recently everyone we observe that there is increase in oil price, and the statistics says that transportation sector alone accounts for 1/3 of oil consumption. So we are keep importing that oil and we are spending huge money for that the oil import. And then this is the high time we have to switch over from that fuel-based vehicle to that electric vehicle. These are all the two important points. One is why we want to move from fossil fuel to renewable sources, and then transition of fuel-based vehicle to the electric vehicle. These are all the two important points we have to consider our future energy requirement and all. So this slide shows that as all of you know, that the solar and wind are the well-known renewable sources available now for that energy generation, and extensively now they are generating energy from these sources. Once you are generating the energy from these renewable sources, you should have that energy storage devices to store that energy, and whenever you need, you can use that energy from that particular devices. Lithium-ion battery and then supercapacitor are considered as the promising energy storage devices. Both are having its own advantage and disadvantages. Lithium-ion battery or store energy through electrochemical redox reaction. So that is that the Faradic reaction involved during charging and discharging process, whereas supercapacitor or store energy at the surface of the electrode. It is purely a non-Faradic reaction. There is no chemical reaction involved in that during charge and discharge process. Next couple of slides, I would like to explain about what are all the basic component involved in the battery and the working principles of lithium-ion battery. So when it comes to the definition of the battery, a battery is transducer which converts the chemical energy of its active material into electrical energy through electrochemical redox reaction. Battery classified into two categories. One is primary battery and another one is secondary battery. The former is not rechargeable, whereas the later one is rechargeable battery. When it comes to that, the component, there are four important components in the lithium-ion battery. The anode material, usually graphite, carbon-based material used as a anode material. And then the second one is cathode material. Usually lithium-based compounds are used as a cathode material. So when you want to prepare that electrode, you have to mix with the binder and the carbon black and then coat it on that the aluminum foil, you will get that the cathode electrode. Similarly for anode, if you are coating on that copper foil, and then you will get that anode electrode. And then third important component is electrolyte, usually lithium salt, which is dissolved in the carbonate solvent used as electrolyte, LiPF6, usually used in all lithium-ion cells. It is ionically conductive, electrically non-conductive, and then the separator. So which is used to avoid the short circuit between cathode and then anode. All polymer film is used as a separator. This slide shows that the various cathode and then anode which are being extensively used in the lithium-ion battery. The high voltage compounds are cathode, and then the low voltage compounds are anode material. So one may ask, what is the advantage of lithium-ion battery over other secondary batteries? If you can see the energy density of lithium-ion battery, it is in the range of 150 to 250 watt-hour per kg, because the cell voltage of this lithium-ion battery, it is high. Whereas if you can see the other secondary battery like nickel, cadmium, lead acid and all, the energy density is not even 100 watt-hour per kg, because their cell voltage is very less. So similar like energy density, there are other factors including self-discharge cycle life and then high rate performance also superior compared to that other secondary batteries. That is why lithium-ion batteries is being extensively used in that all the electronic items. So next two slides, I'll be explaining about the basic principle involved in that lithium-ion batteries. Having said in the earlier slide, lithium-ion battery having four important components. This is cathode material, usually lithium-based compound, and then anode is the graphite material, and then in between separator is placed between cathode and then anode, and then also electrolyte also it is there. When you are powering your device, please carefully see this animation. So the lithium-ion get oxidized and then it diffuses from cathode to anode and it is intercalated into the graphite. Whereas whatever the electron which is generated in that oxidation reaction at the positive electrode, it goes and then charging our devices. if you closely see that the animation, there are two kinetics it is happening. One is lithium-ion diffusion kinetics, another one is electron transport kinetics. If one could able to control the kinetics of this lithium-ion and electron transport during charging discharging process, you could able to make that a fast charging battery. That's what the nano size cathode material and then good conductive medium are essential to increase the diffusion kinetics of ions and electrons. This is the example what is happening when we are using that lithium iron phosphate as a cathode material in that lithium ion cell. How that so lithium ion is deintercalated from that lithium iron phosphate, and lithium, whatever lithium it is generated from the cathode, it is intercalated into that negative electrode, and then whatever the electron which is generated, it is used for charging our devices. This slide shows that what is happening during discharge. Exactly reverse thing it is happening. Whatever the electron which is generated from the oxidation at the anode side, it is powering our devices. Whatever the lithium ion which is intercalated during charge process, it goes back to the cathode sides, and so this is where the mechanism involved in that. So simply speaking, the charging and then discharging process involve lithium ion settling between cathode and the anode. So during charging from cathode to anode, it is intercalation taking place, and then during discharging process, the intercalation of lithium ion from anode to cathode, it is taking place. This is mainly because of that lithium ion shuttling between cathode and the anode. This slide shows that the applications of lithium-ion battery, as all of you know, that it is extensively used for that all the electronic items, including laptop, mobile phone, and then camera. And then recently in India, we started using this lithium-ion battery for light vehicle, and then starting from light vehicle to that high-end electric vehicle. This slide is very important. What is the advantage of this electric vehicle over the fuel-based vehicles? Forbes India, they have given very interesting the statistic about that the cost comparison between the fuel vehicle versus electric vehicle, considering average person drive 10,000 kilometers per year. So for example, if you can see the cost of electric vehicle, the cost is about 8 lakhs. Nearly half of the cost it goes for the battery. Battery cost is 3 lakhs. So when you are charging your the electric vehicle, per charge you have to spend nearly 50 rupees. When you are charging one time, you have to drive nearly 100 kilometers. For driving 10,000 kilometers per year, you have to spend only 5,000 rupees per year. On the other hand, if you can see that the fuel-based vehicle, the cost of that vehicle is less than that the electric vehicle. Considering that mileage 10 kilometers per liter when you are riding within the city, and then considering that the fuel price of about 100 per liter, and then if you are calculating the driving running cost for driving 10,000 kilometers per year, you have to spend nearly 1 lakh per year. So if you are comparing that running cost, the running cost for driving that electric vehicle is 20 times lesser than that running cost of the fuel-based vehicle. That is that the significant advantage of using that the electric vehicle. So the other advantage, as you know, that there is no green gas emission when you are using that electric vehicle. And recently government is giving that a lot of the benefits for the customer who are all buying that electric vehicle. There is a tax exemption of up to rupees 1,50,000 is available, and there is a reduction in that GST, and as well as the registration fees and road tax. This way that the government is trying to encourage the customer to buy that the electric vehicle. So you may ask why we need that indigenous battery material technology. So as having said earlier, current EV technologies in India are operated with the imported lithium-ion battery pack. There is no single manufacturer in India to make or to produce that lithium-ion cells. So whenever you are importing lithium-ion battery, it is always expensive. So in order to bring down the cost, the indigenous development of battery technology is need of the hour to bring down the cost of lithium-ion battery or cell model. And then when you, if you are seeing that the components of lithium-ion cell, there are various components are exist in that lithium-ion battery. So which component or which area we have to concentrate to bring down that the overall cost of that lithium-ion cell? This pie chart, it will give you the idea. So if you can see the pie chart, nearly 43% of cost coming from that cathode and then anode material. And then if we can develop that cost effective and then cathode and then anode material, you can bring down that overall cost of the cell, that it will reflect in the final cost of the electric vehicle. That is where ARCI, we have been focusing on that development of low cost and large scale process for making that lithium-ion battery cathode and then anode material. So ARCI, we have been working on that two objective. One is we want to set up that the pilot plant facility for making lithium-ion cell. The other objective is for developing that indigenous material, which is used as a raw material for making lithium-ion cells. So this is the lithium-ion pilot plant facility which we have established at our ARCI Chennai Center. And starting from that, the mixing, coating, calendaring, all that process, we have that equipment, and we have established this facility for converting powder into that cells. And so this lithium-ion based compounds are very sensitive to the moisture and the oxygen, and we have to use that humidity control room for the fabrication of lithium-ion cells. And we have established 30% RH room and 0.5% RH room for that coating as well as lithium-ion cell fabrication. And we have extensively use that the facility for making that different capacity of that lithium-ion cells, starting from that 5 ampere to that 50 ampere our lithium-ion cell we have fabricated from our facility. So the thing is, whatever the cell we made from our pilot plant facility using that imported lithium-ion battery material. So when you are keep importing lithium-ion battery material, there are a lot of challenges. So after some time, the supplier may not be ready to supply that material. Even if you are insisting to supply the material, the cost, it may be high. So, and then suddenly some company, they are stopping the production. So there are, you have to depend on someone for making lithium-ion cell. If you have your own lithium-ion battery material production, and then you don't need to worry about anything supply chain issue for making lithium-ion cell. That is where we are considering that the development of indigenous materials is very much essential to meet our requirement. So in ARCI, we have been working on that various cathode material like LFP, NMC, and then LNMO. In the anode material, we have been working on lithium titanate, silicon tin-based materials. We work on that, we do a lot of optimization and then validate this material in the lab scale. And then subsequently, we do that all the upscaling. And then later we supply this material to our pilot plant facility to make that the lithium-ion cell using our indigenous material. So next few slides, I'll be presenting that the development of cathode material at ARCI. So there are two well-known cathode chemistry being used in that lithium-ion battery. One is LiFePO4, another one is NMC. If you can see the energy density of LiFePO4 it is about 180 watt-hour per kg, whereas that NMC energy density is about 250 watt-hour per kg. Because the LFP cell voltage is only 3.2 volt, whereas NMC voltage is higher compared to the LFP. That is the reason it is showing that high energy density. If you have the high energy density, you have that the long driving range, that and all, you may use for that long driving range. But if you, other than driving range, it is very important that factor is that is safety. So coming into the other parameter like cycle life, cycle life, it will come nearly 80% capacity, it will retain even after 3000 cycle. Whereas NMC battery, it can retain only 80% capacity per 1000 cycle. So nearly it may come about 10 years, it will come that LFP based the cathode lithium ion cells. Another important thing, recently you might have seen that a lot of fire accident in that two-wheeler. So when you are using that, you have to use that cathode chemistry according to your climatic conditions. So some two-wheeler, they have used the NMC chemistry. So NMC cathode have been used for making lithium-ion cell. If you can see that NMC cell, it is stable only up to 30 degrees centigrade. Considering our Indian climatic condition in that the summer and all, it goes beyond 50 degrees centigrade. So when there is a high temperature in the surrounding, obviously the temperature inside the battery, it increases, and then a lot of highly flammable liquids are there inside lithium ion cell. For example, that electrolyte and then carbonate solvents are highly flammable. And whenever there is a temperature increase in the lithium ion battery, first it damages that separator, and subsequently whatever that the electrolyte also getting that decomposed, and a lot of exothermic reaction it is happening, and then temperature is keep building inside the lithium ion cell. Finally the explosion, it is taking place. So you have to select that the suitable cathode chemistry which is suitable for Indian climatic condition. If you can see the thermal stability of LiFePO4, it is stable up to 60 degrees centigrade. So as per as we know that LFP chemistry is suitable for that our Indian climatic condition. If you want to use that NMC, you can use NMC subject to providing that thermal management system. You should have that proper cooling system so that the temperature of the battery, it will be maintained with that room temperature using that thermal cooling system and all. Again, it will add up the cost. Cost wise, it may not be competitive. So that is the reason we always suggest that to use that LFP based chemistry which is suitable for our Indian climatic condition. Other than that, the chemical stability, it is having the superior chemical stability, and then cost wise it is cheaper compared to the NMC chemistry. So what I want to say is high thermal stability of LFP is advantage for tropical country like India. And then BYD and then CATL, these are all the Chinese company. They are the pioneer in this development of LFP based batteries. And then Tata and Mahindra also, they are planning to use that LFP chemistry for their lithium-ion battery pack. And then recent, the government of India target is 60 million EVs by 2030. So considering that 50% of electric vehicle, if we are using that LFP chemistry, nearly 1 to 3 lakh tons of LFP material is required to visualize or to materialize our the government target. As of now, there is no company to make this LiFePO4 or any cathode material in India. So this is very important to develop our own material technology. That is the reason ARCI, we have been working on that development of indigenous lithium-ion battery material by large-scale process. The strategy which we have adopted is we want to prepare that nano-size LiFePO4 to increase the lithium-ion diffusion kinetics during charging discharging process, and we want to have that uniform carbon coating to improve that electron transport during that charge discharge process. That is the strategy we have adopted. Initially, we have used two-step process. First, what we have done is we have synthesized that nano-size LiFePO4 cathode material using our pilot plant facility called plain spray pyrolysis. What we do is we dispose all lithium, iron, phosphorus salts in that alcohol solution. Finally, we introduce into that high temperature flame where it undergoes the pyrolysis. Subsequently, all that the melting, nucleation, everything it takes place. Finally, we get that nano-size LiFePO4 particle. As it is LiFePO4 particle, it is not electrochemically active. You need to have kind of carbon coating on LiFePO4. We have done that carbon coating on that second step, and then we could be able to do that the uniform carbon coating with the thickness of 5 to 6 nanometer. And then finally, we have validated the material performance in the half cell mode. This is the graph. It shows that what is the capacity of ARC developed LiFePO4. The x-axis is number of cycle, and then y-axis is how much current it can deliver per gram of material. If you can see that ARCI material, it can able to deliver 141 milliampere per gram, which is close to the capacity of one of the commercial material which we obtained from the TODA. And the capacity of material is much better than that other commercial material, which is showing only 89 milliampere hour per gram. Even though we are able to synthesize the material which is at par with the commercial material performance and all, there are challenges when we are using two-step process. When you are using two-step process, it is expensive process, and then practical adaptability is very challenged. So that we realized that the importance of using that single step process for making that carbon coated LiFePO4 in single step. And then we have adopted that high energy milling process for making that carbon coated LiFePO4 in a single step process. In high energy milling process, we take all that dry material, lithium, iron, phosphorus, along with the LiFePO4 raw material. We also add that the carbon precursors along with this raw material, and then finally we do that the milling. So the milling, during that milling, the high velocity, the kinetic energy has been generated because of the collisions of the balls, and then whenever the particle goes between the balls, and it is fractured into that smaller particle. And then after that the milling, once we reduce the particle size of the raw material, then we do that the heating to get that the carbon coated LiFePO4. And then here we have adopted that high energy milling, high energy attrition milling unit for milling of the raw material. And then we have done that various optimization, including that precursor ratio, milling time, and then speed to ball to powder ratio. Lot of optimization we have done in the milling as well as heating. Finally, we could be able to synthesize that carbon coated LiFePO4 by single step process. The advantage of this process is in situ carbon coating. Both the LiFePO4 in situ carbon coating done in a single step process, ease of upscaling. So here it is single step process, and there is no solvent involved in that during the process, and that way it is the mass production. It is easy, and it is cost effective process, and easily adaptable to large scale and upscaling to produce that the mass production or large quantity of material. This slide shows that the physicochemical properties of our ARCI developed LiFePO4 material. As you can see that we could be able to synthesize that 50 to 100 nanometer size LiFePO4 particle, and the TEM image says that the LiFePO4 particle are embedded into the carbon network. The carbon which is coated on LiFePO4 is around 5 to 6 nanometers, and then this carbon is amorphous in nature, and it is having that pure olivine structure without any secondary phase formation and all. And here we have listed out what are all the other the physicochemical parameters. And so once you are developed that material in lab scale, it is the technology is not about only lab scale R&D. You have to do that upscaling of the process which you have developed at the lab scale, and then we try to do that large scale demonstration of our ARCI developed LiFePO4 material. So we don't have the large scale facility, and then we have tie up with one private industry, and we use their the milling as well as the furnace facility. And with that facility, we could be able to demonstrate our ARCI developed LFP process for making 20 kg LFP per the batch. So this is that large scale attrition milling unit where we can do that 20 kg milling raw material is possible, and we have done that 15 kg LFP raw material. So we have done that milling. Subsequently, we have done that the compaction of that milled material, and since we are using that the applying vacuum during the heating, as if you use the powder, it may fly. That is the reason we are compacting, and then the compact has been heated in that furnace to get that the final LiFePO4, and this is our entire team, the industry as well as ARCI team involved for that the production of LiFePO4. And here I would like to show the performance of ARCI LFP material in that point cell level as well as the actual lithium-ion cells. So this shows that the typical charge discharge profile of LiFePO4, and if you can see the capacity of ARCI LFP material at 1C. 1C means you are giving that 1 hour for charging, 1 hour for discharging. When you are giving that this current rating, what is the capacity of ARCI LFP material is about 139 milliampere hour per gram, which is close to that commercial material. Whereas when it comes to that the high charging rate 5C, hardly you are giving 12 minutes for charging, 12 minutes for discharging. ARCI material able to deliver that more than 100 milliampere hour per gram, whereas the commercial material, it is showing that less capacity, even less than 100 milliampere hour per gram. So we want to evaluate our material in that actual lithium-ion cell, and we have fabricated lithium-ion cell using graphite as a anode material, and this is the capacity. So what we have done is we have compared that the performance of cell which is made from the commercial LFP material, and this is the capacity of ARCI cell which is giving 1.5 ampere hour, whereas cell made from commercial LFP giving 1.8 ampere hour, slightly higher than that ARCI cell. But if you can see the capacity retention, ARCI cell could be able to retain 92% of initial capacity, whereas the commercial cell, it can able to deliver only 77% of its capacity. So here what I would like to summarize here, we successfully developed that the process, and then we have demonstrated for large scale and validate the material in lab scale as well as actual lithium-ion cells. So starting from that material to device, we have done that, and then this process we have filed a patent. And last year we have transferred this technology to the one private industries, and we have successfully demonstrated the process to the private industry. Now they are looking for that the global exclusive rights, and then we have been working on that. It is not only technology transfer to the private industry, we are extending our technical support for setting up the plant in Hyderabad. They are planning to set up the plant with a capacity of 1 ton per day. So we are supporting for that. Chairman, how many minutes I can continue?
Sir, the webinar is actually from 10:30 to 11:30, sir.
Okay.
Yes, sir. Thank you, sir.
Another 10 minutes I will complete, madam.
Yes, sir. Yes, sir.
So like LiFePO4, we have been also working on that anode material. In general, in the commercial lithium-ion cell, graphite is used as a anode material. Lithium titanate also is a promising anode because it is there is no strain during charge discharge profile, and there is no ACA layer formation, and it is safe, non-toxic, and long cycle life. The advantage is it can go about 20,000 cycle, but compared to the graphite, the energy density of LTO based battery is slightly lesser, but it is having several advantages, kind of fast charging and all. Considering that aspect, we have been working on the development of lithium titanate anode material. Similar solid state process we have been adopted for that synthesis of lithium titanate, and we have used that high energy attrition milling unit for milling of lithium and the titanium raw material. Subsequently, we have done the heating to synthesize lithium titanate. And when we validate the performance, both commercial as well as ARCI developed the LTO material showing the performance more than 160 milliampere hour per gram. The important thing I want to highlight here
ARCI, an autonomous R&D center of the Department of Science and Technology, DST, Government of India. ARCI is primarily focused on developing nationally unique technologies through its application-oriented research and transferring them to Indian industry for commercialization. ARCI has been continuously evolving the formats by which we may engage with stakeholders from other R&D labs, academic institutions, and industrial organizations to develop technologies and innovative solutions suited for the changing world. ARCI presently has 11 centers of excellence. Its COEs have consistently worked towards development of new materials and processes, providing solutions to industrial users and transfer of technology for commercialization, including the PEF fuel cell system for stationary and mobile applications, oxide dispersion strengthened ODSTs for high temperature applications, nano-composite functional coatings for efficient solar thermal systems, joining technologies for automotive light weighting, coating technologies for power plants, ultra-fast laser microprocessing to create features in the sub-micron sizes, high-performance ceramic components for applications ranging from energy-efficient air heaters to SiC-based substrates for optical applications. True to its mantra, translating research to technology, ARCI has successfully transferred 16 technologies to 28 receivers and more than 150 technological applications for industrial and strategic use. Detonation spray coating technology in late 1990s for aerospace, textile and hydropower sectors, which is still continuing to evolve with advanced features.
My experience is very good with that organization. And recently we have signed an agreement for laser cladding technology, which is a new development in Indian market.
Anti-mine boots for security personnel. Nano-materials for textiles finishes with antibacterial and self-cleaning ability when exposed to sunlight.
ARCI is a friendly, collaborative, and a competent materials partner. ARCI helped us to take this idea from mind to market. Silver technology was indigenously developed and patented worldwide. This helped in improving social wellness and hygiene. We received 2 national awards, one from TDB, another one from Nano India. We thank and appreciate ARCI for their contribution for this global project.
Silica aerogels based flexible sheets with outstanding properties for industrial thermal insulation. Apart from these, ARCI continues to strengthen its patent portfolio with filing of more than 100 national and international patent applications. ARCI serves as a springboard for inculcating interest in the young minds to opt for research as their career. There are innovative approaches afoot in the areas of materials for energy and environment through cost-effective solar cells, storage batteries, and supercapacitors for electric vehicles, low-cost fuel cells, magnetic materials, thermoelectric devices to recover waste energy from exhaust, nano-composite coatings to replace chrome-based coatings, advanced manufacturing processes such as additive manufacturing, laser micro-machining, high-energy milling, high-performance ceramics, new steels for use in fusion reactor and supercritical thermal power plants, and improved machining tools.
ARCI 20 is now very enthusiastically poised. We would like to elevate the research enterprise at ARCI by further intensifying our interactions with industries and user organizations, other R&D institutions, and together synergistically convert our knowledge into technology which is commercializable and usable. We have also resolved to align ourselves with national missions like Make in India. The strengths and capabilities that we have built over the years, we are sure and confident that we will be able to aptly respond to any materials technology related needs of the country and the industry, and there is a promise from Team ARCI.
ARCI is evolving and innovating continuously to contribute to the field of application of materials and manufacturing technologies in general.
Thank you, sir.
Thank
Sir,
you.
would you like to take a few questions from the audience?
Yeah, I'm ready.
Sir, there is a question from Alagappa University, Karaikudi. There is a research scholar there working on activated carbons. So he is asking about how to choose the activating agents when he prepares the activated carbon.
Yeah, okay. There are two kinds of activation involved in that. One is physical activation, another one is chemical activation. So when you are doing that physical activation, always you will end up with a very poor yield. Chemical activation, you will end up with that high yield. But at the same time, after that, the heating process and all, again, you have to remove that whatever the chemical agent. We usually use the potassium hydroxide. That has to be removed. For that, you have to use that some acid and then other solvent and all you have to use. But what I would say is your end target application is important. Suppose for our application, we want to have kind of high crystalline carbon with both having that micro and mesoporous structure. That is the reason we have tried with the chemical activation. When we tried with the physical activation, but we are also getting the property, but not that much. The micro and then mesoporous controlling and all, it is very difficult when we are using that physical activation process. Whereas when we are doing that chemical activation process, you can nicely fine tune this, all the porosity, crystallinity, all the things that you can do that. So that chemical activation may be that ideal method for making that supercapacitor grade carbon. But the cost wise, so you have to make it how minimum you can use that chemical agent and all, that you have to do kind of optimization. Then you can make it that economic process, even if you are using that chemical activation process.
Okay, sir. Thank you, sir. And there are other two questions in general. Dr. Pandishwari and the other, they want to start their research, or they would like to do something on energy storage materials. They would like to ask you on what material should they focus on? What is the current trend? For example, what is being used as anode? What is being used as cathode with respect to lithium ion? On what they should start their research on?
So, madam, there are many components. As I showed in my presentation, there are many components starting from cathode, anode, electrolyte, separator. There are many groups have been all over the world, and in India, many IITs, NITs, all the R&D institutes, they have been working on that cathode development and then anode. Coming into the cathode, so the LiFePO4 and then NMC, these are all that the promising two cathode chemistry is being used in the lithium ion cell. And then if you can develop that the material with the low cost and with the high performance without compromising any the stability and all, so then so you can transfer your material technology. But developing that cost effective, which is cost competitive with the commercial material, always challenging. Whatever the China they are giving, it is all cheaper one. So competing with that, so you have to really work on that to develop that cost effective process. So LFP and then NMC, these two chemistry they can try. And another one is the anode side. There are silicon based composite and LTO based anode, and then tin based. All these have been trying now. So because all this material, for example, silicon based composite is a high capacity anode material which can be used for lithium sulfur battery application and all. So this is about the anode. And electrolyte and separator, usually many groups they are not working on that the electrolyte and separator. Mostly all it is commercially available. Another important thing what we focus on in future is the recycling of lithium-ion cells. Now we started using all the lithium-ion cell for various applications, starting from electronic gadget, and now in another 2 to 5 years, there are many electric vehicle is going to come after usage. You have to keep. So then, if you are having technology to recycle that lithium-ion battery, that would be fantastic. So one has to focus on that lithium-ion recycling also in the future. That is the one topic they can focus on that. But a lot of chemistry involved in that. Who are having the chemistry background, they can take up that lithium-ion cell recycling, that topic.
Thank you, sir. So the audience, sir is talking about replenishing the lithium ions like lithium metal, because right now the research is on is in the peak. So everyone would be using the material and we'll be facing such kind of scarcity. So
Yeah.
if anyone works upon how to recycle, so it's going to be very, very important in this present scenario. Thank you very much, sir. And some audience who do not have much background, they're just asking you a simple question about what is the difference between using this hydrogen storage and such kind of like battery materials, whatever we talked today.
Yeah. So main thing is the hydrogen storage. Also our government is introduced hydrogen based that transport and all. The problem is you can generate the hydrogen, even the hydrogen production also there is efficiency that it is very low. And another big thing is how you transport this hydrogen to one place to another place. That is the biggest challenge when you are even if you are generating it is you cannot keep it idle in one place. So you have to transport the lot of pressure variation. All it is a problem when you are transporting hydrogen. That are all the two issues. But hydrogen it is also very green energy. It can be used. But these are all the challenges are there. Every field, whether it is lithium-ion battery powered electric vehicle or hydrogen powered vehicle, everything challenge is there, and then we have to address that. So that hydrogen energy when you are using, these two challenges are there. One is the efficiency is low, and another one is how to transport. The transportation issues are big issues.
Yes, sir. Thank you very much, sir. And one last question. There is some kind of aversion towards using of electrical vehicles. Like many who belong to non-technical background or in general, seeing such kind of accidents or something. So they feel that EVs are slightly dangerous. So what is your say upon it and why is it so?
So 2 years before, even our all the company who are all promoting electric vehicle also, they have kind of I would say zero knowledge about what is the chemistry involved in that lithium-ion cells and all. After this accident, recently so many accidents happened in that only in the two-wheeler sector. You may not have seen any accident in the four-wheeler. Four-wheeler, for them all, it is a billion market, and if anything goes wrong, so obviously that customer they will hesitate to buy that. But in the two-wheeler, it is not that much high investment market. Who are having money just to import that lithium-ion cell without knowing what is the chemistry, what is the capacity, nothing. Then just they put that, and then so they promoted that all the electric vehicle, it has come into the market. As I mentioned in the presentation, there are two chemistry. One is LFP, another one is NMC. So our Indian climatic condition, according to our climatic condition, you have to select that cathode chemistry. So the LFP chemistry, it is stable up to 60 degrees centigrade, whereas the other chemistry can be stable only up to 30 degrees centigrade. When you are using this NMC chemistry based lithium-ion battery pack, so all that accident it happens. But after this accident, our people, they come to know that okay, this is the chemistry which is suitable for our condition. And LFP chemistry, NMC chemistry, we are not against NMC chemistry. You can use NMC chemistry provided you have the proper thermal management or cooling system. Already people are saying that the electric vehicle cost is expensive. When you are adding another cooling system, again the price it will go up. So again, cost competitive wise, it is not that much good. So that is the reason people are using that LFP based chemistry nowadays. But the only issue is, as I mentioned, the energy density is slightly lesser compared to that NMC based chemistry. For example, So you are driving a LFP battery pack. If you are using, you can drive about 80 kilometer. And then, whereas if you are using NMC based lithium-ion battery pack, you can go up to 120 kilometer. That for two-wheeler who is riding more than 10 kilometer in a day, right? So in that case, my safety is important more than that what the driving range I am getting. So I don't want to compromise the safety of my electric vehicle by only the getting that advantage in that driving range. That's what people they have realized now. And then more people now, even customer, they are asking what is the difference between these two. So mostly even customer, all the company recently they have been educated about this the chemistry of lithium-ion cell, which is there in that, and then what chemistry is suitable for our Indian climatic condition and all. Government also they have taken that initiative. So we are being a member of Bharat Indian Standard. So we have been working on that the chemistry which is suitable for. We have given our recommendation to the ministry, and then we suggested all these points to that ministry. Soon they are going to come that clear policy on that. So you have to use this particular chemistry. And another important thing is other accident what happened recently is without knowing that the quality of the cell, simply our people they have been purchased and then assembled a mod. And then worst thing what we came to know that the secondary use of the cell has been imported from the abroad. That is the poor thing. So government made a policy. You have to first to go through all the testing and then make sure, okay, this is the capacity of the cell. Then you have to use that cell for assembly and all. There are several policy has been made that they are going to implement to avoid all this kind of accident in future.
Oh, thank you, sir, for enlightening all of us. Dear audience, we came to know that the safety measures and the deep chemistry involved with this is very important. And ARCI and sir, they have all given the guidelines to the Ministry of India, and soon a proper policy would be implemented. And we are going to enter into this silent revolution of EVs. Sir, thank you very much for spending time with us, sir. Audience, let us thank the speaker with clapping of hands. Let's open our video so that we get the opportunity to take a photo with our scientist of the day. After the group photo, I would be putting up the feedback link.
Thank you, madam. Thank you, audience, for your patience for the last 1 hour.
Sir, we are thanking you. You have spent this kind of time with us. Thank you, sir. Okay, so whoever.
Thank you.
Yeah, so I will take a screenshot. I will say 1, 2. Then the audience can say like this or something. You can say like this so that we can have a group photo with the speaker. Yes, ready? 1, 2, 3. Once more, because there are other pages also. Ready? 1, 2, 3. Once more, please. There are many people in the third page also. Ready? 1, 2, 3. Okay, once more. Last time. Ready? 1, 2, 3. Yes. Thank you very much. I have posted the feedback link in the chat box. Kindly fill the feedback link within an hour or so. Thank you very much.
Thank you, madam. Thank you, madam. I am signing off. Thank you.
Thanks. Dear participants, the feedback link is there in the chat box. I would be posting it again and again for the next 5 minutes in case if you miss it. Kindly fill it immediately. There are some students who could not attend the webinar today due to like unexpected number of participants trying to log in. So we have recorded the video. So by evening, we will provide the YouTube link for this lecture, and we will provide all necessary certificates for them as well. Please kindly do not worry about this. So after finishing your filling of the feedback link, you can leave the session.